Our talk's going to be discussing how we believe a Kubernetes operator can make your relational databases safer. One housekeeping item I would like to share is that there's going to be quite a lot of topics covered in our slides. Depending on your background, some things may be completely new, some things may be things that you're very familiar with. But because there's so many of them, we'd like to kind of keep the pace in our talk. So if you have specific questions or comments, please just kind of collect them, and we can talk through them at the end. We don't really have another talk starting here for another hour, like it's lunch after our talk ends. So we can take questions for as long as you'd like. So let's get started. Maybe we'll quickly introduce ourselves first. Peter?
Sure. Hi, I'm Peter Farr. I'm a software engineer working at PlanetScale on PlanetScale's operators, and one of which I'll be talking with you about today.
All right. My name is Liz Van Dijk. I'm a solution architect at PlanetScale as well. I'm fairly new to Kubernetes as well as Vitess, but I've lived in MySQL world for the past 8 years. I used to work at Percona. So this is a kind of a new, strange room for me to be presenting in. But yeah, I hope we can still marry those concepts with some success. Yeah, so a little word about PlanetScale. So PlanetScale is a database company. We love databases. We've been founded by the creators of Vitess in January 2018. And as a company, we offer Vitess support, all kinds of services around Vitess. We try to popularize it as a project. We've also built a Vitess operator for Kubernetes, and we're going to be discussing that in particular in this talk. And as you may have seen, if you've attended our colleague Abi's talk yesterday, we also create a database as a service on top of these technologies ourselves in a concept that we like to call eating our own dog food. The fact that we have a product running on these projects makes sure that we're extra invested in making sure that they're in good shape. We're VC funded. We're mostly based out of Mountain View. I myself am based out of Europe, though, so if there's any strange language quirks, please blame it on that. So who remembers the times when MySQL didn't even scale beyond 4 cores? There's quite a few people here. So there's quite a few long-time MySQL users. So that was about 15 years ago. And at that point in its life, it was already 10 years old. So I guess what I'm trying to say is databases or relational databases are old. A very long-standing, very mature technology. If you go and look at dbengine.com's top 5 most used relational databases today, those are still listed as Oracle, MySQL, SQL Server, PostgreSQL, and DB2. And of all of those, MySQL is the youngest. So at a ripe age of 25 years old, it's still the youngest of the ones that are most commonly in use today. So why are we still using these technologies? Why do we rely on something that's, been around for so long? When it comes to our business data, we still favor reliability and maturity over fancy features. So it is just something it is the kind of use case that's grown out of maturity and many, many years of optimizations and lessons learned that's causing us to keep choosing relational databases as a platform for our applications. Over the past decade, we've seen a lot of performance gains thanks to new hardware developments, like there's better CPU architectures, we have faster RAM, particularly we've got faster SSDs. But on the whole, the internals of these relational database systems haven't really evolved very much. They're still very much reliant on a tight coupling between RAM and disk, so they're very tightly interrelated. And that just makes it easiest to accomplish, or that makes it easiest to keep them working within the bounds of a single machine. It's kind of difficult to scale that beyond the boundaries. So 15 years ago, a single beefy server might have been enough to cover most workloads, but when Web 2.0 came around, everything changed. It kind of started challenging our throughput requirements, especially our storage needs. phenomenon like Black Friday or Singles Day started hitting our servers, requiring massive scale up and down as needed. So it kind of, those kinds of workload requirements sparked a huge evolution within our resource provisioning platforms. So we started seeing developments like virtualization and container orchestration as a direct result of those needs. So nowadays, what we're seeing as a result of those technologies coming through, SREs are managing environments that are a lot more flexible. They're loosely coupled, they're flexible across the entire stack, they're automatically configured, they are provisioned as needed. But databases have always struggled in this kind of environment because their internals have not really adapted. There's been a sudden explosion of really highly specialized, scalable data solutions, like NoSQL, various NoSQL solutions that helped us, try and overcome that gap, try and close the gap. But tech companies are still kind of struggling to overcome that scalability need. So most NoSQL solutions are choosing to erode ACID requirements in favor of flexibility, which kind of makes them a difficult fit for our typical relational database needs. Most of them also lack the maturity that we talked about earlier that relational databases already have. So that's kind of been the challenging part. I'm sorry, I'm kind of struggling with my remote here a little bit. So zooming in on MySQL, our company is highly focused on MySQL, so we're going to be taking a closer look in particular at this. For many years now, despite our ability to improve MySQL scalability beyond 4 cores, luckily there's been some improvement there. The only feature, or the only scaling feature that's really included out of the box with MySQL is still replication. And there's a couple of key challenges that we're still faced with. So the MySQL team has mostly chosen to stay agnostic as to the stack that we build around MySQL to improve its scalability and its reliability. And there have been a few recommended stacks that have evolved around MySQL to offer features that we're missing here. But we're still faced with a couple of challenges that are just very difficult to overcome. So as of today, we want to say that the key challenges that are faced with people running MySQL in a rapidly growing environment are still very much the same as they were 10 years ago. Those key challenges, I'm just going to list them up real quick right here. So we're struggling to deal with rapid data growth. Scaling writes in particular has always been a challenge with MySQL. I want to say scaling reads has been more or less a solved problem because we do have replication available, but scaling writes has always been quite difficult. There's nothing built into MySQL to help us look at query distribution. So your workload coming in, there's no smart way to spread it across multiple nodes. Automating failover is also a process that we need to look at ourselves. Infrastructure provisioning, clearly, this does not happen. That's not something that MySQL handles at all. And service configuration discovery, as well as automating of workloads redistribution as needed. Say, even in a planned scenario when you want to redistribute your workloads because you need to take a specific machine offline, there's nothing provided within MySQL that helps you cover that need. So, talking about Vitess. Vitess is the open source project that I mentioned earlier. PlanetScale is a very big supporter of it. And it tries to tackle most or some of these key challenges within MySQL. And the reason that we're covering it is our demo and our premise is based on using Vitess as a scaling solution for MySQL. So About 10 years ago, Vitess was started development at YouTube. It's created as a middleware layer on top of MySQL. And as it started growing, YouTube faced some really unique data-related challenges, clearly. And rather than try and reinvent the wheel and build something new, the team there decided to try and adapt MySQL. As YouTube was acquired by Google, the framework also needed to be able to plug in easily into Google's orchestration environment, which is why we actually get to claim that Vitess was ready for Kubernetes even before Kubernetes was officially launched. Sorry. So Vitess was built for scale. In essence, like when it started out, it was built specifically to allow for sharding. So it's massively scalable, highly available as a result of that. We'll get into the details of why we call it that. And it is fully based on MySQL. So it's not trying to reinvent the wheel. It's not creating any new storage engines. We're kind of relying on the 25 years of experience making MySQL run well with production workloads. Some quick stats. I'm not going to get into this too deeply, but what's maybe interesting to know is that Vitess itself is already quite a mature project. It's existed for 10 years, and it is as a part of the CNCF portfolio. Right now, it's the only relational database project that's considered graduated, so alongside Kubernetes. It's one of those projects that's considered battle-tested in real production environments at a couple of very large industry players. So a couple of logos that might look familiar. These are all key adopters of Vitess. They have Vitess running as part of their critical infrastructure. And just to clarify, that PlanetScale is not the only ones developing Vitess. A lot of these companies actually employ active contributors and project maintainers. So, given that Vitess is based on MySQL, it should be pretty simple, right? Well, in some respects, it is. But as you can see from the diagram, there's quite a lot of components that go into creating this simplicity of use. To the left of the dotted line, you can see everything that makes up your own application. And your application communicates directly with something that we call the VT gate. And VT gate is kind of what makes Vitess represent itself to your application as a single monolithic MySQL database. So the reason that Vitess is easy to adopt and integrate into your application is because it is fairly interchangeable with MySQL. You connect to it with your normal connectors, it speaks MySQL, and it presents itself as MySQL. So it's a very comfortable, recognizable environment. As you can see, though, on the back end, there's quite a lot more logic there to keep in mind, and there's a lot of infrastructure that's involved in keeping Vitess up and running. Let's see. Very quickly to cover some of the elements that go into Vitess. So as we mentioned, we have VT Gate. It's a stateless proxy. It's the entry point into our cluster. This is what your application communicates with. It represents however many shards you have on the back end as a completely monolithic MySQL database. You can also spin up as many of them in parallel as needed to help you deal with rapidly evolving workloads. And it speaks SQL. It allows a couple of Vitess-specific commands as well, but on the whole, you're just integrating with that as with a normal MySQL database. Of the challenges that we were discussing earlier, VTGate primarily helps us address the query distribution issue, as well as it playing a very large role in our failover automation. So, what is a key space and what is a shard in Vitess? So coming from MySQL, you're probably familiar with the concept of a schema, which is a logical description of the structure that makes up your actual database. In Vitess, a key space is the analog of that. Because Vitess supports sharding transparently, a key space can be composed of one or multiple shards. A shard will contain a portion of your data contained in the database and is by itself composed of multiple elements that helps keep it durable and available. So the shards are designed in a durable way individually, and spreading your data across multiple shards in multiple availability zones can help you split risk geographically. Looking back at the key challenges slide, and we'll review those later again, sharding primarily helps us cope with massive data growth and helps boost our availability in failure situations as well. So what are these shards actually made of? And this is where things become a little more familiar again if you're used to working with MySQL. We call the individual components that make up a shard Vitess Tablets, and by itself, what you need to understand about that is that MySQL is not sharding aware. It's not aware that it's running as a part of Vitess. So we have a tiny sidecar process called Vitess Tablet to help Vitess manage the individual MySQL D processes. This pair could run anywhere you'd want to run MySQL. So you can run it on bare metal, you can run it on a VM, or inside of a container. And Vitess doesn't really care about the underlying infrastructure there. All it controls is MySQL. But looking inside of a single shard, we'll usually have multiple tablets running inside of it to ensure high availability. And in a healthy state, all of those tablets are going to be able to receive reads. VTGate's going to make the decision about where to send a given query based on the tablet's assigned role. And those roles might look familiar as well if you're used to using MySQL replication, because effectively they're built entirely on top of that technology. So it's Vitess managing MySQL replication to assign different roles to tablets within its shards. At any point, one shard will have, or a shard will have one VT tablet or one tablet that is marked as the master. And that's going to be used as VTGate to direct write queries. And there might be multiple other replicas which are being directed by a standard replication to keep their data in sync with the master. To ensure, in case of disastrous failure of the master, to make sure that we always have one replica tablet that's fully up to date with the master. Within Vitess, though we don't require it, we do recommend that you use semi-sync, the semi-sync functionality within MySQL, to ensure that while you're performing transactions or while you're doing write transactions to the master, at least one of its replicas will acknowledge having received the instructions of that transaction. So in case of a master failure, at least we'll have one replica that is as closely up to date as possible, so it can serve as a strong failover target. Now, we mentioned availability zones earlier and the fact that you can shard across multiple availability zones. So there's one more concept that we want to cover here. Vitess offers something like Self. You can use that to align with your Google or with your cloud provider's availability zones. So you can use them to assign shards or parts of shards to different availability zones and kind of craft your disaster recovery strategy around that. To help us split up shards and key spaces efficiently, the operator has another subdivision called Replica Pools. So I just want to point out that the picture there that you might see, a single shard can actually break down into more parts that we didn't really get into here. But those are called Replica Pools, and Peter's going to get into why those are important and how they can be used to help our operator improve availability of our service. Now, bringing it back to the overall architecture slide, there's a lot that goes into running Vitess. I guess that's kind of the summary here. And by itself, it addresses a lot of the key challenges that we highlighted earlier about running and scaling MySQL. But it still requires an immense amount of infrastructure and configuration to keep it all together. And as of right now, we're still kind of faced with the challenge of bridging the gap between throwing a completely unconfigured virtual machine at this cluster and getting it up and running as a productive member. So very quickly, like these are the items that we've already covered in our challenges list. Right now we're putting automating failover as kind of a partially covered. Vitess puts us in a position to make failover a lot easier, but by default it doesn't actually automate failover. So the scaffolding is in place, so to speak. So here's where our talk finally starts to fit into the container track and the topic of this assigned track. Turns out Kubernetes is built exactly for the purpose of the points that we haven't covered yet. So as we know, it's a production-grade orchestrator. It's seen a huge growth of popularity in recent years, and it helps us effectively manage complex applications at a massive scale. So it solves most of our problems related to deployment of complex topology and infrastructure through orchestration. And historically, it's always been considered best suited for stateless workloads. And because, how we mentioned earlier, databases keep so much of their state in memory, Kubernetes has not historically been considered a safe platform for a database to run in. Before I hand it off to Peter, let me just cover two more concepts for those of you who are not too familiar with Kubernetes just yet. We're going to be mentioning these quite often. Workloads in Kubernetes are handled by predefined groups of services that are bundled together with the purpose of executing very specific tasks. Say, to run a web server, we'll need the actual web server process, but we also need networking. We may need a little bit of local storage. So there's a couple of different components that go into the delivery of what a web server's job actually is. So we take all of those elements and we define them as a pod. And the pods are the smallest way that Kubernetes provides to compartmentalize service. Now, pods, or workloads specifically, do need workers to execute as well. And in Kubernetes, those resources are defined as a node. A node as a worker machine could be any physical resource that you have available. So that could be a bare metal machine, or it could be a virtual machine. Interesting to know is Kubernetes actually schedules proactively the pods themselves onto nodes that have availability, that have extra capacity available. So, Peter, would you like to take over?
Sure. So just picking back up where Liz left off, what is a typical use case of Kubernetes? So like traditionally, they're used for stateless web servers, right? It's really easy to scale those up or down. If resources like pods become unhealthy, Kubernetes can just tear those down, spin up new ones. But that kind of approach is really problematic if those pods are stateful. We can't really just tear down our databases at will. We could be losing important customer data. And so this is sort of why traditionally Kubernetes has been thought of as a poor choice for stateful applications. But luckily, there is a modern solution. And that is operators. So what is an operator? It's essentially a custom application for Kubernetes where we take complete and full control, and it replaces a human operator, kind of like it's like a little human DevOps operator in your system doing work for you. And because of that, it removes an aspect of human error, which is great. Humans are very error prone. It improves our system reliability as a result, and it allows us, by having complete control, to deploy stateful applications safely. So let's dig in just a little bit more into operators. In the early days of the Operator SDK, it used very different design principles than the modern Operator SDK, sort of a toolbox for you to build your own operators. So in the early days, it was built around this idea of event handlers, which did turn out to be a bit problematic. It kind of encouraged this very imperative design pattern where when you notice that something goes wrong in your system, you need to send someone, almost like a command, like, hey, you over here, go fix this thing. The problem with that is okay, what if we miss an event? Or what if an event comes out of time and we're suddenly applying, a command at the wrong point in time, and our system state just gets all messed up. So this sort of led to some fragile design patterns that didn't really scale very well. So how are things different now? So in the modern Operator SDK, it's sort of built around this idea of independent state reconciliation. So we have independent actors, which are basically controllers, and each controller will reconcile a different subset of your system state, and they work totally independently. This sort of encourages more of a declarative pattern, because the way that these controllers tend to work, which we'll get into, is that they ask Kubernetes, like, hey, give me this object, and I will look at this object. I will look at user intent, and I will compare it to system state, and I myself will decide if there is a difference and where I need to reconcile those differences. And this tends to be much better at scale, which encourages more robust and scalable design principles. So what is the anatomy, essentially, of an operator? They're very simple. I kind of think of them as just two parts. So the first part is what we call the API. And this might not fit into like the classical definition of an API, but in the world of Kubernetes, this is called your API. And it's sort of, what should the YAML look like? Right? Like when I write YAML for the operator, what is the structure of that YAML? And I will define that with a Go object. So let's just take a quick look at a really simple example. So here's something that we use. It is used to store information about what the intended state of a shard is in Vitess. Ignore the metadata fields at the top. Let's just look at the two fields at the bottom. So spec and status. So these spec is used to define what is the intended state of my system as defined by my user. Status, on the other hand, is what is the calculated state of the system at this point in time. So don't try to read this, but this is just a quick example of how we got some YAML, and it roughly fits the Go struct on the right that's annotated. It'll get serialized into some nice Go objects for us to play around with. So what do we do once we have these Go objects? Well, we have controllers that are responsible for state reconciliation. So like how we just saw that there's a Vitess Shard object, we have a Vitess Shard controller that's responsible for reconciling user intent, what the user wants the shard to look like, with what is the current state of our system right now. Each controller, importantly, has a function called Reconcile. Let's just go through sort of the simple steps of, like, what does any reconcile function do? So the first step in any reconcile function is it will fetch the object. Like in this example, we'll fetch the Vitess Shard object that we care about. Then we will reconcile system state to match user's intent. Pretty simple. And then we'll recompute the status, system state. And if we recompute the status, then that object has to get put back into the lock server that backs Kubernetes etcd. And then we requeue the reconcile. And requeue could be on a standard polling frequency, or it could be a more complicated requeuing strategy that you use. So this is a quick example. No need to try to read all the code, but those are roughly the steps. 1, 2, 3, and 4 are kind of the same step. The way we do status updates is they persist when we update status automatically, and then we requeue at the end. So let's just recap a little bit more about operators. So again, operators reconcile user intent with the state of the world. They're typically one controller per object. Or are they? So this is probably something you won't hear in other places, but we've found that it's actually really useful to have multiple controllers per object. A really good example is that we have a Vitess Shard controller, but we also have a Vitess Shard replication controller, and that controller will reconcile the replication state. So it's sort of a subset of the shard. But it's actually highly useful to split these out, because you can have independent actors that reconcile different relationships of objects as opposed to only reconciling states of objects themselves. And operators are really built around this paradigm of show your state. Each controller can compute what they think the state of the world is. Anyone can have access to that and make independent conclusions and decisions about that state, which makes for a very robust and powerful system. So what is Orchestrator? Like, why is this slide even here? Well, Orchestrator is a replication topology manager for MySQL. And we just said a second ago that we have this Vitess Shard replication controller. Well, okay, why are we even trying to reconcile replication when we have such a fantastic tool like Orchestrator that's so popular in the community? Orchestrator is already used very heavily in Vitess deployments. The way it works is it pulls all of your MySQL D instances in your system, and based on what it finds, it stores that in its own backing database. So it has its own MySQL backing database that it puts all this information in, and then it runs very giant queries against that backing database to try to understand if we are currently in a failure state and if we should do something about it. And as a result of that, it handles a multitude of known replication-based failure states. So why reinvent the wheel? What are some drawbacks to this? Well, it's a highly stateful design, for one, because it stores all this information in its own MySQL database. It also means that you have to consider the availability of Orchestrator itself. So you don't only have to consider the availability of your primary system, but also of Orchestrator. And if Orchestrator isn't available, then your system isn't that available either. This adds some additional complexity, especially in the world of Vitess, where we're already dealing with Vitess, MySQL, Kubernetes, and an operator. And it has in our world, it has another drawback, which is that Vitess topology becomes eventually consistent. So in the world of Vitess, we have a lock server, a highly available lock server that stores all of the topology data for Vitess. If Orchestrator comes in and decides to fix something at the MySQL level, it can take a little bit of time for Vitess to learn and catch up and update its records as well. So it's better if we can instruct Vitess directly to do the repairs for us, as opposed to having a tool that goes under the hood and talks to MySQL. So one specific failure case that Orchestrator handles that's probably the most important one to us is a state known as dead master. So like what is dead master? Well, it's obviously when your master is dead, and we can define that by it being totally unreachable by all replicas. So we can't talk to it, no replicas can talk to it, no one knows that it exists anymore. Whether it exists or not is irrelevant because we need a healthy master up and running. So once we've detected this state, if it persists long enough, then we have to act on it. The way that Orchestrator works is it'll find the most caught up replica, and then it'll elect that to become the master. But we found out that actually this is a really easy problem to solve using Kubernetes' own API. So without further ado, I will give you guys a demo. It's actually, do you mind holding that? I just realized it's hard to hold the mic while you're demoing. Great. So actually, let me first show you this fantastic demo that we made with lots of dogs that you can rate. So there are these really cute dogs, and you're like, oh, that's a pretty good one. And you can just rate them all day long. It's fantastic. So we got some real dogs, and these dogs are running on a Vitess database using our operator in Kubernetes. And oh, that's a cute one. All right, wonderful. So what we will do is we will cause some mass chaos and destruction and watch everything gracefully recover. So first, let's just take a look at our system. So I'm just going to get my cluster info. And if we scroll up here, we can see all these wonderful pods. We have, as Liz brought up, we have some VT gates. We have VTCTLD, which is our control plane. And we got a bunch of tablets. Fantastic. So we got to find out which one of these tablets is our master. Well, in the world of Kubernetes, as we said, we kind of have this idea of show your state. So we can look at the state of our system right now. So let's just take a look at. This is single sharded, just to make it easy and obvious that we are definitely creating havoc on the only database we have. So if we look at this Vitess shard object, there's a few things to note. So let's first look at something that I'm going to come up to later after the demo with some slides. But here's where we store some custom condition types about our system. So we have a dead master condition. And right now we're showing that we have not yet detected it. The failover is too fast for me to show you that this is flipped to true, but I can show you with logs for sure that the whole process is happening. But let's move on down to status so we can go ahead and find what our master is. So there we are, master alias. So it's our master is in GCP US West 1C, and it has this identifier. So to save you the pain of a very long command, I did write a little helper script that execs into master for me. What this is going to do is we're just executing into the MySQL container of our master tablet pod. So we're inside here. How do we create mass chaos and destruction? Well, one thing you might think, I thought, oh boy, this is easy. I'm just going to kill MySQL. Well, nope, it just recovers right away, easy peasy, no problem. But we can be a little more evil about it. So we can go to where Vitess stores the InnoDB data file. And let's just take a look at that. Can you guys see that? Great. IB data 1. So the easiest way is we'll just overwrite it with, we'll just zero it out. Fantastic. And that is zeroed out. No chaos still. Everything's fine, surprisingly. But what we'll do is we'll start right now writing dogs in a multi-threaded little dog writer that I built. So we got 8 threads running. They're spaced out, but they're just filling in some dogs for us, writing those to the daughter base. And so what we'll do now is if we kill MySQL, it should catastrophically fail. So we will kill, is that 2425? Great. And watch over here on the right, we got a rejected query, and those are basically hanging, all those queries, and we picked right back up. So let's take a second to analyze a little bit, and hear what happened. So as soon as we killed master, we had one rejected query. The threads keep trying to write dogs, but they're hanging. And they're hanging because the VT gate has a buffering process. So the VT gate will buffer on begins. We won't tell you, obviously, that we've committed your data. We can't talk to anyone to commit your data. But we will basically just ensure that we don't have mass hangups, which could create problems. So we're just saying, hey, hold on a second. We're gonna repair things, and we'll get you back in order. And once that happens, you can see here our max response time is about 5 seconds. So in the way I built it currently, which is very easy to adapt, if dead master state exists for longer than 4 seconds, then we go ahead and find the most caught up replica. We promote that to master, and we set all replication of that new one. Because we have semi-sync turned on, it also means that we do have to wait for replicas to begin replication again, because we won't tell you that any transactions are committed until a replica has told us that they've caught up. And having semi-sync on in this case also has the additional benefit that we can guarantee that we have found that the most caught up replica we found has all of the transactions, and we didn't lose any data in the process. So let's see. I guess I'll flip on back to, oh wait, I guess one thing that is interesting to see is just, is just that we can see that the master did change. Yep. So you can see here the master we're connected to as an identifier of 386321 blah blah blah. And this one that we now have is 3439196432. We go back to get our pods again. Let's just get pods. We can identify that there are definitely 2 tablets of that type. So we have those right here. So we definitely did flip from one tablet over to the other, and we're back to being able to write traffic. So let's pop on back to the slides, and we can walk a bit through more exactly how this all worked out. Oh, oh. Yes, but there. Awesome. Oh, this is going to be, oh, yes.
Just a reminder.
All right, so how does this work? So we have 2 independent circuits. The first one is a detection circuit. The way this works is logically the same way that Orchestrator works, which is that we pull the replicas and we ask them, hey, do you think master is dead? If we get totally unanimous response, everyone thinks it's dead, then we say, great, we've entered into a dead master state. That state gets stored in a shard condition object. What is a condition object? Well, you've probably seen some condition objects from the core Kubernetes library, if you've worked much with Kubernetes. A really common one you've probably seen is a pod condition object. This can store different states about our pod, and it can store, also importantly, how long those states have persisted for. So here's that. For the purpose of what we're working with, we mostly care about the first 3. So for now, we can ignore reason and message. So we have a type of condition that we care about. We have a status. That's actually true or false condition. It's a bool essentially. And last transition time is when did we last transition from false to true or from true to false. So we realized that we can use this concept and we can just build our own condition objects and do really cool things with them. Oops. So we did. And we built a Vitess shard condition object, which can store special types that we're aware of. One of those types is a dead master condition. And when we go from false to true, we can record when that happened. And based on that information, any independent actor can analyze that and understand how long we've been in that failure state for. And if they want to, they can act on it. So one of those actors is a separate independent circuit that runs a recovery process. It basically just checks every second, hey, are we in dead master state right now? And if so, have we exceeded the maximum acceptable duration that we've configured? If that's happened, then we will find the most caught up replica. And in Vitess land, we run an internal function called emergency reparent. So emergency reparent will do all the dirty work of promoting that replica to master and setting all other replicas to replicate off of the new master. So why was this better in Kubernetes? Why not just stick to the world of Orchestrator? Well, then the really nice thing about Kubernetes is that it's really built for state reconciliation. So it's a really, really nice medium for doing this kind of work in. You have access to the state of all of your components all the time based on that principle of show your state that we talked about. As a result of that, it's very, very easy to write automation around state reconciliation. It's also super easy to discover all replicas. This has traditionally been a kind of a hard problem to solve. In the world of Kubernetes, it doesn't really matter what our current system is. It matters what the intended state of the system is. So if a replica has gone down, we can still know for sure whether we have or have not communicated with all replicas when we're trying to get a quorum over certain failure cases that we might be experiencing. And, like I said, very easy to build state reconciliation features. And conditioned objects are really awesome. You should try and create your own. They're really, really powerful. And, OK, so why is this also better with operators? Well, we can use an operator to easily manage multiple failure domains. As Liz had discussed earlier, there's this replica pool concept that I'll dig a little bit deeper into. So replica pools is an operator-specific concept. It's actually not something that Vitess knows about. We came up with this concept that you could create pools of replicas that you can assign to different availability zones or different failure domains if you want to define cell in a different format. And also, we can pair this with semisync. So semisync can be configured across availability zones. This means that you could suffer a complete availability zone failure and have complete assurance that your data is in a availability zone that has survived, and that this dead master failure recovery feature will find a most caught up replica in a surviving availability zone, promote it to master, and your system will be up and serving traffic in no time. So, oops. Yep, all that stuff I just said on a slide. Great. So what are some other safety guarantees we have? Well, one thing is that pods can quickly be moved to other nodes during health degradation. So in the real world, we don't really often see complete and total catastrophic failure. We usually see health degradation of nodes over time, and that health degradation can be monitored with metrics. Typically what happens is real engineers can be notified about that health degradation, and then we can essentially run a single command in Kubernetes to do what's called a node drain. Sounds really like a convoluted term. Basically just means that we mark that node as not schedulable. All the pods get evicted, and our operator will do the work then of scheduling them to a healthy node. What are some other generic safety guarantees? This might not be, all these might not be operator Kubernetes specific, but some general things we do to try to be a little bit extra safe is that the MySQL data itself is stored on cloud block storage like EBS. So node failure doesn't necessarily mean that you're going to get data corruption. The EBS usually will detach, or we also can detach the EBS for things like rolling updates. Another benefit in terms of safety guarantees around rolling updates is that with an operator specifically, you can design a lot of logic, for instance, around doing updates in a very safe way. So for instance, if we're trying to update tablets, we can write in logic that says, only update them one at a time, ensure we always have enough healthy serving tablets up and running in the system to be able to execute this update, wait until it's completed, make sure that tablet comes back online and is serving again, and now we suddenly have enough healthy ones to execute the next one. And so we can kind of move through the system and roll updates through in a very safe way using our operator. And lastly, periodic backups. I'd say this is a little step above a cron job. You can take periodic backups, obviously, using just a cron job. The nice thing about doing it with an operator is that they are guaranteed periodic backups. So we can retry on failure. We can ensure that data is safe to use and good to use, and ensure that we always have, like if you back up every 12 hours, we ensure that no matter what, every 12 hours you have a usable and safe backup ready to go. So as Liz brought up earlier, we had a lot of these really big key challenges, right? And Vitess sort of checked the first 3 boxes and gave us hooks for handling the 4th. Within our operator in Kubernetes, we can complete the full failover story. We can easily do infrastructure provisioning. We have super easy service discovery, configuration, and discoverability of anything in our system. And we can also automatically redistribute workloads. Pods can be distributed to other nodes when they become unhealthy. And so we sort of solved the whole gamut of challenges that we had with trying to scale MySQL in the first place. Great. So that's the talk. Before we get to questions, just point out that if you want to check out our open source operator, please do so. Please build your own operators. They are awesome. Check out the Operator SDK. It has really good docs, really easy to use. If you want to learn more about Vitess, you can learn that at our website. We have a super open and welcoming Slack community where our CTO, who is one of the original creators of Vitess, is there, happy to answer questions at any point in time.
Even at 3 a.m.
Yes. Sure.
So you mentioned that you use polling to have slave nodes protect the master set, right?
Mm-hmm.
So it's just like simple HTTP request polling?
The polling goes through the VT tablet, but it's essentially running show slave status against all the MySQL instances, which is the same thing that Orchestrator does. But it is moving through the tablet. Yeah. Sure, I could look. I think, I believe it's over Unix socket, actually. Yeah. Oh, sorry.
The question was using poll. Okay. So I was asking if instead of having the worker nodes poll the master nodes, you could potentially implement some sort of interrupt pattern. I was thinking it uses TCP sockets, but apparently it uses Unix sockets. So.
Cool. Thank you very much for the question. Good question. Or, I don't know if we should run mics back and forth. Okay.
Can you replicate from a standard traditional MySQL database instance into a Vitess-based instance, say running
so the question was if you can replicate from a standard MySQL D instances into a Vitess-backed one, for instance, and back and forth.
In theory, yes. Well, we can replicate from a normal MySQL server into Vitess, and it's actually one of the migration paths that are recommended. If you want to gradually understand how Vitess is going to be a fit for your workload, it's one of the ways that you can start trickling in queries and run them against Vitess to make sure that everything works well. The other way around, I don't see, well, I mean, I suppose you could have a single MySQL server link up to one of the slower replicas in Vitess, but I don't see why exactly you would want to do that necessarily. But yeah, it is possible, and it's something that's done quite often.
Cool. Yes. Here, maybe I'll run this down.
I've been working with MySQL for quite long. Some challenges are with MySQL cluster. high availability, and multi-master replication, and how do you reconcile the data inconsistencies in a multi-master replication and cluster? Does it fit into this Kubernetes architecture?
Unless I'm totally mistaken, as far as I know, we don't do multi-master. Am I?
So the way that that's solved is Vitess actually only accepts one tablet to take on the master role within a given shard. So we can parallelize writes across multiple shards, but not within a given shard. We only have one tablet that's set up as a master, and only that one will receive writes. So that's how you avoid that inconsistency. Now, thanks to semi-sync, we also make sure that at least one replica tablet is always fully caught up to that master. So once we do failover, we know that that replica will have a completely accurate set of data there as well. So, all right? Go ahead.
Yeah, just a really dumb question. So something like Vitess, could you do like key-based distributed querying, like you could with like Redshift or Splunk, or do the queries run on a single node?
I mean, in theory, these are just MySQL instances, so yes, you could run any kinds of read queries against them, however you'd like to distribute them yourself. VT-Gate, if you run your queries through VT-Gate, VT-Gate will be the one to make the decision, but you could query the nodes, you could query the tablets individually, but yeah, I mean, only for reads would that be recommended. Right. So that's why we have multiple roles assigned to our tablets. Like we have some tablets that we keep as failover targets. So those are kept very closely in sync with the master, but we also have some analytics replicas that could be used for longer running queries that have, they should have a full and complete copy of the data as well. But those are the ones that technically you could lock up with longer running queries. And you won't be affecting the rest of the system. All right. Any more questions? I think that wraps it up. Thank you very much.